I don't see Alexis or Chad or Bridget or Reagan or Sally or Jaron or Edward. And that's it. There's Sally. Okay. Getting started, maybe. There we go. This is a picture one of my friends, reposted on Facebook. One of those things it's seen 500 times. But it's perfectly appropriate for what we're doing now. Now, of course, the joke, this is why women live longer than men. Is what they're doing OSHA approved? No. Why is that not OSHA approved? Because you only have one, you can only have one man on a ladder. You can't have three men on the ladder. That's just, okay. It's not so much about the numbers, although there probably is truth to that. But more importantly, people keep rolling in. Okay, I still don't see Chad or Edward. More importantly, what's keeping the dude in the basketball jersey from falling? There's what? Torque. He's standing there over the overhang. If you look at him, his center of mass is going to be somewhere around here. So we can treat the force of gravity as acting straight down from there. And all that's underneath him is that ladder, which we know is very light. The ladder is going to have its center of mass somewhere around here, but that's a small force. But then we have the force of this guy going around here, and this guy going here. And so when you look at that, you have to add up the torques. And if the net torque is a positive torque, well, then there's going to be a force normal over here. Let me change to blue. Ideally, there would be a force normal acting on this region here. Acting on the entire region, right? And ideally, that force normal would be there keeping it from, doing anything funny. What happens if the net torque is negative? Hopefully I said positive first time because that was, The net torque is negative, he goes down. What's the equation for torque? Okay. Perpendicular distance times force. You notice I said the distance first and then the force. The reason is because of the actual equation for torque that we'll see, I think, on the very next slide. So in this situation, if the sum of the torques equals 0, then he'll be in equilibrium and it won't rotate on him and he'll be good. Right? Normal would be what provides the excess torque to get you to 0 if you had a positive torque. If it's a negative torque, he's just falling. Okay, kind of fun to look at. We could use this equation because all the forces are vertical and all the distances are horizontal. Then just like we did in lab, the equation is just R times F because it's RF sine theta to get the perpendicular part. Okay, oh no, I had this before. Look how tricky I was with my title being rotated too. I thought I was very tricky. The Leaning Tower of Pisa is an equilibrium situation. Now, I got a bunch of pictures here because I thought it was very interesting. If you look at the history of the Leaning Tower, when they started construction over here around 1200 or so AD, they built it vertically. Crazy thought, right? Build a building so it goes straight up. But then it started tilting. Why do you suppose it started tilting? Because of what? The foundation. The foundation, You know, the wise man built it. Oh, I don't have a picture with the foundation. I looked at a lot of pictures. A wise man built his house upon the rock. That's not what they built the Leaning Tower of Pisa on. It's got, you can look at all the stuff under the foundation if you go to either one of those two websites that I have there. But it started tilting. You can see they went from actually the construction was 1173 to 1178. I could have read that off my graphic here. And then they went for nearly 100 years with no construction, during which time it started tilting. And then they said, hey, that's okay. We can double the height. Went from 3 stories to 6 stories. And then they went another nearly 100 years. They said, hey, let's finish it off. Now, if you look at architectural designs and plans, they actually try to curve it to make up for its leaning aspects. Would you say the Leaning Tower of Pisa is in equilibrium? I see answers both ways. What are our 2 conditions for equilibrium? Number 1, net force has to be 0, which means that the acceleration is 0. So I'm going to write it that way. I'm going to write condition 1, acceleration equals 0. Is the acceleration 0 for this tower? Okay. Condition 2. What was condition 2? Net torque is 0. And the equivalent statement to acceleration is 0. Turns out to be the angular acceleration that we've already learned, alpha, is 0. That is the rate of rotation. Whoops. Stay there. The rate of the rotation is not changing. Is the rate of rotation of the leaning tower changing? It's approximately 0. And in fact, up until 1993, it was tilting a millimeter or 2 more each year. So it had a pretty constant angular velocity, but the angular acceleration was pretty much 0. Of course, once it got too far, it would start to pick up. So one would say, okay, it was in equilibrium. In 1993, it was leaning out 5.4 meters. Get back to just normal zoom here. So the edge here, and if you extended this up the edge here, it was offset by 5.4 meters. Or if you take the center line was offset by 5.4 meters from bottom to top. That's kind of excessive in my opinion. And so in 1993, they started a retrofit to get this thing so it won't fall over. So they put some wires to hold it up, and then they dug underneath and they did some drainage things, because it actually, as water flowed underneath, it would seasonally change the amount it tipped because of the water coming and going. Now I have that action going on in my house, right? You might notice that you have cracks in the walls that get bigger and smaller through the season because of water. Well, they had that action going on. So they did some drainage fixing, and then they also shored up the foundation. And after they finished their work, it went back 38 centimeters from how much it had tipped. And since they finished the work in 2001 or something, it's come back another little over 2 centimeters. So it's basically tipped only 5 meters now, where it was 5.4 is the actual number that was tipped before. Okay, so it's still an equilibrium problem. If you look at the foundation, what forces are acting on that foundation?
Normal force.
Okay, basically we have a normal force. We're going to have forces going like this on the foundation, and then the center mass, which it tells us right here, the center mass is 22.6 meters above ground. So somewhere around here is the center mass. Change the color here back to red. So somewhere around here we have the center mass. And so the force of gravity can be treated as if it's acting there. Now a question that we all want to know is, how much would it have to tip before it became unstable, before it went out of equilibrium and started falling? If you were just trying to figure this out, no physics background, if you were just trying to figure this out, how would you answer how much you think it can tip before it fall over?
Would be like, oh, the center of gravity would no longer be supported. So like if you have something that's being balanced, and then you adjust it so the center of gravity is no longer over the support directly, then it.
Okay, that's the answer I would have given as well. As long as the center of mass is between the supports, so our supports run basically from here to here. So as long as the center of mass, that was not a vertical line. As long as the center mass is between these lines, I would expect it to stay upright. So it can tip, a fair amount more than it was right there and still be standing. Gets scarier and scarier. And, what would happen if it tipped more and more? Well, given that its foundation wasn't strong enough, as it tips more, what do you suppose is happening to these forces? Yeah, this one here is going to have to grow and grow as it tips more. Why? To give you the counter torque, because the center of mass up here is giving a bigger and bigger torque that would be, as you look at this picture, a negative torque. And so you'd have to have a bigger and bigger positive torque for this. So this force would have to get bigger and bigger and bigger. Well, there's only eventually you're not going to be able to supply that, and she'll start toppling just because that support isn't strong enough, even though it technically would still be stable if that support was strong enough. Now, we are going to do some more study on equilibrium, but I believe I have a clicker question before we do any more study on equilibrium. So, oh nope, I got this first, then the clicker question. This here is what I said I think next. We have the torque, right? I've said I think next, and I was wrong twice. Here's the equation for torque. The full and complete equation for torque is this equation right here. We use the Greek letter tau for torque. That's a lowercase tau. A capital tau looks like a T. So we have the torque is equal to R vector. The next thing we say cross. Not times, cross. And then the force vector. Now, if you think about it, vectors have direction. I can't multiply north by east. Right? Multiplying north by east doesn't give me anything that computes in my brain. So when we deal with things that are multiplying vectors, we have two ways of multiplying vectors. The two ways are the dot product, also known as the scalar product, which we've already seen. Work was equal to force dot distance. And what did that mean when I did the dot product? That was just multiplying the parallel parts. Yes. And the name scalar product tells you it's going to give you a scalar for the answer. Now we have what we call a cross product. Which is also called a vector product. And the cross product example, torque vector is equal to R vector cross F vector. Now let's look at the units before I do anything else. Force times distance. So this had units of newtons times meters, which we call joules. Distance times force. So that has also units of newtons times meters, which we do not call joules. So with work and energy, we call it joules. With torque, even though the units are exactly the same, we don't ever use the word joule for torque. It's incorrect to call a torque having units of joules, even though joules mean Newton meters. Joule is reserved for energy. So torque has units of newtons times meters, the same as the units for work. But it's something completely different. Now, it's a cross product, it's a vector product, it's going to give us a direction for the answer, as you can see by having the vector sign over torque. So how do you get the direction for this, and how do you do the multiplication? First, the dot product was multiplying the parallel parts, the cross product is multiplying the perpendicular parts. So if I have something that has the force vector is like this, and the R vector is like this, then I want to find the perpendicular parts. Historically, what have we done to find the perpendicular parts? Break things into components. So I could break either one of these into components. Let's say the angle between the two is theta. And so if I want to break these into components, I will break R into its R parallel and R perpendicular. I want the perpendicular part, so I'm only going to calculate that one. And notice my triangle would be the same here. So this side of the triangle, is that adjacent or opposite? It's opposite. So that means to get the R perpendicular, that's going to be R times sine of the angle between R and F. So to calculate the magnitude of the torque, so if I write torque without the vector sign, that's R perpendicular times force, which is equal to RF times sine of the angle between them. That's how you can get the magnitude. Now for the direction. For the direction, we use the right-hand rule. Now every time I teach the right-hand rule, I go back to when I was in college. I had a classmate, and our teacher in math class, because that's ideally where you would have learned the right-hand rule, is teaching us how to apply the right-hand rule, and Saeed is sitting here doing it like this. And Dr. O'Brien says, Saeed, you have to use your right hand. Saeed answered, but I'm left-handed. Being left-handed, or suffering from sinistrality, as it were, does not mean that you can arbitrarily change the directions of things. The right hand and the left hand are mirror copies of each other, and you get the opposite direction if you use the wrong hand. So it's important to use the right hand if you're using the right hand rule. And the way the right hand rule works is for any cross product. So here's an example of a cross product. C equals A cross B. And of course, this being written on a computer, they meant those to be bold to indicate the vectors. If I was writing it myself, I would have put vector signs over each one. You take your right hand and put your index finger straight out and put that in the direction of the first item in the cross product. So my cross product is A cross B, so I want my index finger to be in the direction of A. And then orient my hand so I can bend my middle finger in the direction toward B. Now, some rules that people will try to violate sometimes just because they're not thinking. You need to have your middle finger so it bends from straight toward coming out of the palm. Some people will go, I can't do it. I can't hyperextend my fingers. Yeah, some people will do like Ann can do and bend their middle finger back behind toward the back side of their hand. Just because you can do it doesn't mean that's how the right hand rule works. You need to bend them toward the palm. So you orient your hand so your index finger will stay straight and point in the direction of the first one, and so you can bend your middle finger in the direction of the second one. And then your thumb needs to be perpendicular to both of those. So thumb needs to be sticking up and out. And that will tell you the direction of the answer. Okay. Diction, not waiting. Yeah, there you go. It's important to get those straight, and you might have been goofing around. I don't know. But it's important to make sure the index one is the one that goes straight. So, taking as an example a person holding a weight. I'm holding a weight out here at arm's length. the first thing I have to decide is, where's my R? If I were to ask you where's R, what would you answer, Chad?
Your length of your arm?
Okay, length of my arm, going from where to where?
I would say the center of your chest.
Okay, so he says from center of my chest out here. That's very close to what I would have said by default. But when you're actually using this, you need to be more careful. You need to decide, I am calculating the torque about a certain location. And so typically I will calculate the torque about the hinge point. My shoulder is the hinge point, so typically I would say R is going from the hinge point out to here. But I can choose different locations as you did on Friday. So if I have it out here, my R is going about my shoulder from here out to here. So if I'm going to use the right hand rule, R is the first thing in that cross product. So which finger goes in the direction of the first thing? Index. So I need to take my right hand, actually let me use my left hand for the example, so I can use my right hand to explain. So now R is going from my shoulder out there, so I take my right hand, orient so my finger is pointing the direction of R. My hand right now can rotate like this, just that index finger has to point that way. But then I have the second part. I have to then be able to orient my fingers so they point the direction of the force. What direction is the force due to this weight? Down. So I need to take my hand and orient so my index finger is going out to my left, and then so I can bend my middle fingers down. And then what direction is my thumb point? Points to my back. So that means the torque that this weight is creating about my shoulder is pointing that direction. Now, by convention, as you learned, we call that the negative direction. But being more careful, that has a specific direction. So if I held it out here now I won't be able to use my right hand. What direction is the torque about my shoulder now? It's going that direction because you have R is going that direction. You're using your right hand. You take your right hand and orient your middle finger so it points out. Your thumb, or not, so it points down. Your thumb will point toward you. Mine is pointing the wrong direction. Why is mine pointing the wrong direction? Because I'm using the left hand. It illustrates why you can't use your left hand for the right hand rule. Now, you can go ahead and formulate a different way of doing the right hand rule and use your left hand. But we don't confuse things by saying, and here's how you could use your left hand to do the right hand rule. Because that would confuse things. So, torque is R cross F. What would happen if I changed the order? What if I wrote torque is equal to F cross R? If I hold it out here and I put torque as F cross R, what direction would my index finger need to point? Down. And then my middle finger would point that way, and it changes the direction of the torque if you reverse the order. Well, of course, you can't really change the direction of the torque by changing your equation. So it has to be R cross F. Cannot put it F cross R. Now, staying on this slide, that picture there on the left, the wheel. If there is a torque on the wheel, the torque is going to cause it to rotate. This is actually next chapter where we get into the equation. But a torque that is upward is going to make it rotate the way your fingers would curl around the axis. So that's another version of the right-hand rule we're going to use. If the angular acceleration is going the direction my fingers would rotate, my thumb points the direction of the actual angular acceleration. You might wonder, how can a vertical force and a distance that's going this direction provide a torque that's perpendicular to both of those? And the answer really comes from when you're doing rotational motion, you have motion in two of your three coordinate directions. And so the only thing that you could use to define a direction for the rotation is to go perpendicular to both of those. And then we use the right-hand rule to determine which direction we're going to use for the perpendicular direction. And it's kind of arbitrary that we chose the right. I had nothing to do with the decision, clearly. That scientists chose the right-hand rule, and it just sets the signs that they chose the right hand rather than the left hand to standardize. Okay, a quick example here on equilibrium of this burly student holding up a book. Now, you might have very well had a question asking about the muscle force compared to the weight of that book. Well, I did a dumbbell for the question. But how would the force of the muscle compare, you think, based on your knowledge from reading before you came to class, compared to the weight of that book? Same, bigger, or smaller? Bigger. Why would it be bigger? Okay, different lengths from the point of rotation. Torque is R cross F. In this case, they're perpendicular, so we're just going to use R times F since they're perpendicular. But we're going to have the torque created by that biceps muscle has the same magnitude but opposite direction as the torques created by the weight of the arm and the weight of the book. But the weight of the arm and the weight of the book are far out there compared to the position of the biceps, so the biceps can have to produce more force. Now let's actually do this calculation. This is very much like what you did on Friday. So if I take this picture, I can simplify the picture here. This is drawing, instead of showing an arm with a bicep muscle and so on, just showing the forces acting, like you did with the diver. And then we need to choose a place to sum the torques. What was the second condition of equilibrium? The sum of the torques is 0. It does not say the sum of the torques about point A is 0. It just says the sum of the torques is 0. So if the sum of the torques is 0, it doesn't matter what location I sum them apparently, according to what we've said. So I'm free to choose the location to sum the torques. If you're going to do that, you look at the picture and you say, how many forces do I not know? So, Jaron, how many forces do I not know? 2. I don't know what the force is of the elbow, force E. And I don't know what the force is of the bicep, force B. I know the other 2 forces because I know the mass of the arm is 2.5 kilograms. That, of course, tells you where it's located. I know the mass of the book is 4 kilograms. It tells you where it's located. So there are 2 forces I know and 2 that I don't. If I'm going to use the sum of the torques as 0, and I can choose any location, the best location to choose is going to be where one of the unknown forces produces no torque. Now, I'm looking specifically for the force of the muscle. So which position makes sense to make one of those unknown forces have no torque? The elbow. Because if I sum the torques about the elbow, the radius, the distance from where I'm summing the torques to where the force acts, is going to be 0 for the elbow. So using some careful thinking, I make a judicious choice and say, I'm going to sum the torques about this point. And so I always give it a name, A. And so, darn it. I used up the entire page here. Back to normal view. Sum of the torques about A equals 0 equals, and so I just look at each force in its distance. So I'm going to have the force of the bicep times its distance. Its distance we can see from the upper picture is 4.0 centimeters. Is that a positive torque or a negative torque? So which one? Oh, I skipped the first one. I'm sorry. I shouldn't have skipped the first one. I skipped it because it was 0, and when you've done these a lot, you just say, well, that one makes 0. So the first one would have been, yes, force E times 0. And then I have force bicep times 4.0 centimeters. And is that one positive or negative? Positive. Why positive? Okay, because it's going in the counterclockwise direction. If I'd used the right hand rule for that, I would have taken my right hand, put my index finger so it points that way, put my middle finger so it points the direction of the force, which is up. My thumb comes out of the screen, and that's what we consider positive, coming out. So those are two different ways to come to that same conclusion that this would be a positive torque. Okay, then my next one, the weight of the book. Is that going to be a positive or a negative torque? It's a negative because it's now downward. R cross F would be going now into the screen, or it would be a clockwise rotation. So I have minus weight A. Weight A is 2.5 kilograms times 9.8 meters per second squared. And then its distance, which is 16 centimeters. And finally, and I am really out of space, what to do? I'm just going to have to erase this dot product. That was not what I intended to do. To give myself space. Minus the last one, 4.0 kilograms times 9.8 meters per second squared times its distance of 38 centimeters. There we can see all of the information I put in. Notice I use centimeters. What am I going to have for the units of my forces? Kilograms times meters per second squared is what unit? Newtons. I believe I heard that. So I have units of newtons times centimeters. That's not the standard unit of torque. Standard unit would have been newtons times meters. But that's okay because in the end I want to solve for force. And if I take this and calculate it out, can somebody calculate the 2.5 times 9.8 times 16 and then add to that 4 times 9.8 times 38? It's what?
1881.6.
Okay, so I have 1881.6 newtons times centimeters is equal to force of the bicep times 4 centimeters. Well, the last thing I do is divide both sides by 4 centimeters. And we get the force of the bicep muscle here must be equal to, that would be 0 point, no, not 4, not 4, bad math. So it'd be 470.4 newtons. By the way, speaking of bad math and doing problems, last time I did a problem, I got to the end, I said that's not the answer I got before. It's because when I did it before, I forgot a term. What we did in class was correct. When we were calculating the speed the car had to have before the collision, before it hit the brakes, what we did in class was correct. It was my preparation beforehand that was incorrect. Which is a little embarrassing, but hey, I modeled correct problem solving. So the force of the bicep is 470.4 newtons to hold up a combined weight of about 65 newtons. So, that's a big percentage bigger. Now we're going to talk in just a moment about simple machines. Simple machines are things that allow us to do a job hopefully easier. And we calculate the mechanical advantage of a simple machine by taking MA stands for mechanical advantage. It's equal to the force out over the force in. In this case, the force out was what I was holding up. I was holding up the book. The book weighs 4 times 9.8. That's what, 39.2. And the force in, that's going to be the force I had to supply. So that's the force the bicep had to supply. 470.4 newtons. When I look at that, I say that's not a very friendly mechanical advantage. The force I got out of this simple machine, the way my arm works, compared to the force my bicep had to supply, that gives me something that's less than 0.1. Not a very efficient or useful simple machine, you would think, because our muscles have to supply so much more force than the things we can lift. If you compare humans to simians, the attachment points, the points where things like the bicep muscle attaches to the bone, are moved out. So if we were apes instead of humans, we would more likely have the force of the bicep out here. What would that do to the weight that we could lift? If our muscles were exactly the same strength, what would that do to the weight we could lift? It would increase it. So simians, monkeys, and apes, whatever, they can lift heavier things with the same amount of muscle compared to what we can because the attachment points are farther out. And I can't remember all the ins and outs of benefits of each, but we're designed differently than they are, and it affects our relative strengths. If you want to lift something super heavy, you want to curl something super heavier, where would you place it on your arm to be able to curl something super heavy? Okay. Bring it right in here. If I bring it right in here, I could really curl something heavy. Of course, how much would I be lifting it? A very small amount. If we talk about the work done, work is the force times the distance. And so I would have a light or a heavy weight that moves up a very small amount. If I put something out here, I'd have to have a much lighter weight, but I can lift it a much bigger distance. In the end, well, we'll talk about efficiency coming up, but efficiency is going to be relating the works that you do. I don't want to get too far ahead of myself in my lecture here. So, now a question to make sure we all paid attention. Suppose you hold a weight out to your left side of your body with your left arm straight. What direction is the torque created about the shoulder by the weight? So your arm is somewhere out here. Initially I wrote saying it was straight out horizontal, and I said, well, no, it could have been here or here. Yeah, give another 5 seconds. Put an answer in, Sally. Okay, so we had 0, 0, 4, 2, 12, 1, 3. So we have the biggest single group here, and it's a slight majority, said to your rear side. Let me go with Zach, whose team pulled out a victory yesterday. I was sure when that goofball just ran to the end zone, I know he was hurting, but lay down and wait for the half to end with the tie game that you were going to lose. How did you come up with E?
Yes.
How did you come up with that?
I pointed my index finger to the way the arm will point, and then my middle finger, well, this way, when you on that way. So
Yeah.
this one down, that would be the direction of the force, and my thumb would be pointing behind me.
Okay. Which hand did you use?
My right.
The right hand. Okay. By the way, when I went through the interception there in 5 minutes, I thought that was the death knell first. Or twice I thought you guys were going to lose. But no, they couldn't drive for 5 yards to get a field goal. Okay, another clicker question, assuming it comes up. Suppose you hold a weight out to the left side of your body with your left arm straight. What arm angle produces the highest torque? So your options are A, B, C, I feel like I'm doing semaphore, D, E, wait, F, G. There we go. And yes, I've missed a space in G. Okay, we had a bigger agreement this time. 2, 15, 4, 1. Okay, Reagan,
Uh-oh.
did you answer the most common answer here?
I did.
Why?
Well, Zach's, no, I'm just kidding.
Because Zach did, I figured he wouldn't be wrong.
Because when you're holding your arm out, your force is going straight down, and then if you're taking the sine of that force against your R, then that's going to be sine of 90, which is 1, which is going to be the most that you can get.
Okay, good answer. Just looking at the equation, you have the same R, because the distance from your pivot point to where the force is acting is going to be the same for all of them. The same F, because it's just mg. Then you got the sine of the angle. And so when sine of the angle is the maximum value you can reach, which is 1 at 90 degrees, that's going to be maximum. So that's good reason. A second way to reason it, which is the same thing if you slice and dice it, is I have the largest perpendicular distance from my shoulder out there to where the weight is. If it's here or here, it's closer to the shoulder in this direction. So it's the same exact thing. It's just one's looking at the equation alone and one's looking at the picture alone. But we have the same concept in both cases. Right.
Is there a simple way for me to relate this to like my experience, my perception? Like when I hold this thing, nothing's pushing me. Like I don't feel this rotational force making me want to rotate just because I hold this thing. You know, like
well,
I perceive the force.
I'm talking about only a rotation that's vertical. The fact that the torque is to the rear means that it wants to do a vertical rotation.
Okay, but okay. I guess I was thinking that way. Like, is there a way to?
It doesn't mean you want to go like this.
Okay.
The direction of a torque is perpendicular to the direction that things will be rotating. Now, a last question related to this. It's not a clicker question. Let's say I'm doing my curls. If I can, let's say, if I start here and I can get it up to here, does that mean I should be able to get it up to horizontal? Okay, I hear people saying no. Why not?
Because that's the most force.
Yeah, it's going to take the most force to get it held right here horizontal. It'll be less force to do it up at here or down here. It's the middle part that's the most. Now, if you're actually doing weightlifting, there are lots of things that play. You know, the amount of force you can produce is different at different stretches for the muscle. And also you have things, well, you might bend or things like that you can do to change things up. But basically, the hardest part of a curl is the middle part. It's nice to have a lightweight so it's easy to curl it. I often like to do it with heavyweights, show off the spaghetti that I keep under my sleeves. All right, we're getting near the end. We have 5 minutes left. And cheater bar. Now, I don't know about all of you's background, but I come from an agricultural family. And granted, by the time I came along, Dad was the superintendent of agriculture at Monterey Bay Academy. Wasn't doing the whole family farm. We now have a 40-acre almond orchard here. 40 acres, by the way, is postage stamp in terms of orchards. But one of the things we did, we grew corn to chop for silage. And so when it was time to chop that silage, working from before sunup to after sundown, aka while the sun is up. And of course, just like my car out there, by the way, I probably won't be in my office for office hours this afternoon because I hit a nail. And that would happen all the time, especially we got these wagons that are old, got old tires. We'd have flats all the time. And so little peons like me, 13-year-old freshman in high school, Richard, my job was to fix the flats. And so they bring in a wagon with a flat, and I have to take the tire off. Now, if that tire's been on there for a year, it's pretty much rusted in place. And so to get it off, virtually impossible, especially for, I only weighed 130 pounds back then. It's hard to imagine. So we had the breaker bar that you put on the bolt. Now this is on the center. I've taken off the hub instead of taking off the tire. But breaker bar that you put on the bolt, and I could jump on that all day long and not get it off. But we had a 6-foot piece of pipe on the wall. And I put that 6-foot piece of pipe on the breaker bar, and then I would just get out the end, jump up and grab onto it and go, until I got it to either break the wrench or come loose. Now, why was that effective? What's the purpose of that cheater bar, as we call it?
Makes the distance larger.
Makes the distance larger. Why is making the distance larger? Help me? It increases the torque. So here you see somebody who's using just a piece of pipe, just as high-tech as we were. And they even have a breaker bar there, if you look. That's not a socket, it's a breaker bar, or break-over bar. I think technically it's a break-over bar, but we always call them breaker bars. To help get a bigger torque. So that's what the whole cheater bar is about. So, if you don't get this one, that means you just weren't listening. How does a cheater bar help remove a stuck nut? Zach? Uh-oh. We have one person that wasn't Zach that apparently wasn't listening that answered. It increases that lever arm, hence increasing your torque, just like James told us. So it's very beneficial for the farmer and all of us. Which situation is in equilibrium? This is bringing us to our next to last slide. A car parked on the side of a road. This one here, you have multiple correct answers. Put in all the answers you believe are correct and hit enter. Yeah. Okay, we got our answers in, and we have 18 that said the car parked on the side of the road is in equilibrium. 22 that said a car driving on a straight freeway at constant speed is in equilibrium. And 4 that said a car rounding a corner at constant speed is in equilibrium. The 18 are correct and the 22 are correct, but the 4 are not. Why are the 4 not correct? It's accelerating. Just because it's constant speed doesn't mean it's constant velocity. It's accelerating as it goes around the corner. So I am out of time. I guess we won't talk about my last beautiful slide, the teeter-totter. Actually, it's the next last. All right, so I'll see you in lab tomorrow where we'll be studying simple machines like the teeter-totter.